All right, howdy y'all. So in this video, we're going to be doing 8.15. The video is going to be, this proof is going to be broken up into three videos. The first one is going to be the setup, the statement, and the setup to the proof. Then the setup to the proof has two conditions. If you meet both conditions, then then the proof is done. So the proof of each of those conditions is going to be the second and third video of it, whereas right now we're just going to be setting it up and stating the theorem and then setting up the statement. Or setting up the proof. So before we get into the actual statement, we need to define a couple things. So first off, we have this set LF, which we're going to define like this. And what you'll notice is that in here, this feels like a concept of continuity because as we're taking R to be small, we're saying we're taking the integral between points close to X. As they get closer and closer and closer, is this integral actually going to zero? Obviously, if you have something where there's a massive jump to continuity, this thing is going to be staying positive at X. So this has a very much a feel to continuity, but it is a slightly weaker condition than continuity. It is what's called approximately continuous, and the Lebesgue set is going to be the set of all points where this locally continuous, or approximately continuous definition is met. Now, theorem 320 is going to give us that the Lebesgue measure of the complement of a Lebesgue set is going to be 0. And this is the case whenever f lives in L1 lock, which is the locally integrable function. Now, in the statement of our proof, we have that f is living in LP, so obviously it's locally integrable. So we don't necessarily need to consider this last part here because we're definitely within it. But that is where it's defined, and that's what 320 is actually true for. It's a more general case than what we need. So we're going to suppose that the absolute value of phi of x is less than c times 1 plus the magnitude of x raised to the negative n minus epsilon for some c and epsilon greater than 0. Again, this is going to be similar to what we did in the last one, where we used theorem 2.52. So this condition is going to give us that phi lives in L1. So this implies phi lives in L1 by corollary 2.52. And then again, like we did in the last one, we're going to set the integral. Because it lives in L1, we can give it a value, so we're going to set it equal to A. Now, if f lives in LP, and here we're allowing p to be between 1 and infinity inclusive, then the convolution of it with phi sub t defined the same way as the last video is going to AF as t goes down to 0 for all x in the Lebesgue set of f. And again, this is for almost all x because of theorem 320, and because of the definition of the Lebesgue set is for everywhere f is continuous. Again, it is broader than just where everything is continuous, but this is included within this statement. So what we have is, so for the proof, what we're going to do is we're going to set x to be an element in LF. And then for all delta greater than 0, there exists a mu greater than 0 such that we're going to define this I1 to be the integral of y less than r, so the unit ball in R. The R radius ball around the origin, and then we define this guy here. So this is going to be the same one that we used in the last proof, same integral. And then we're going to say that this is going to be less than delta Rn for all r less than mu. And again, this follows from the fact that f lives in LP, and hence, that x lives in the Lebesgue set for f. So what we're going to get is if we define I2 to be the integral outside of it, so same integral, but now when the magnitude of y is greater than mu, we claim two things. We're first going to claim that I is less than a delta, with a independent of delta. So we have that this guy is solely bounded by delta, which means that as delta goes down to 0, we get a delta is going to be eliminated. Whereas if a was, a function of delta, then we have to worry about whether that was actually, as delta went to 0, this was actually going to go to 0. But because it's independent of A is independent of delta, since delta was chosen arbitrarily, this is going to drop I down to 0, and that I2 goes to 0 as t goes to 0. Now, what these two things do, these two claims, so claim 1 for I1 and 2 for I2, is going to be that this magnitude here is obviously less than I1, I2, which implies that the lim sup of this guy is less than alpha than A delta. So this gives us the result that we want, right? Because that's going to give us that this is going here as t goes down to 0, since we're taking a lim sup across t. So, and again, we picked x arbitrarily in LF, and since this lim sup is independent of x is fixed in here, we're getting this to be true for all x in LF. Okay, so in the next video, we're going to prove this statement for I1, and then in the second video, or in the third video, I guess, we're going to prove the secondary statement here that I2 is going down to 0 as t goes to 0. Okay, I will see you guys in a second.